In this illustration, we intend to simulate the consolidation settlement of a multi-layer soil with strip loading in the Abaqus software. The soil is composed of 7 layers. The top layer is sand and the lower layers are clay. The thickness of each layer is 1 meter. As you observe in the picture, the soil is exposed to a strip loading of 100 kilopascal. Actually, we intend to simulate the example 4.8 from some Helvani book in the Abaqus software. In this picture, you observe the geometric shape of soil. In this example, CAM-clay model has been utilized in order to define the properties of clay plasticity, and you can see the properties of clay layers in this table. The purpose of this analysis is to draw a diagram of the consolidation settlement of soil, which can be observed in this picture. I will enter the Abaqus software for simulation. I'll click on Create Part. Here I intend to create geometric shape of soil. I will select the modeling space as 2-dimensional, select a deformable and shell from here, and enter the rough size of the tracing page as 100 and continue. I'll draw a rectangle. The height of soil is 7 meters. And the length of that is 30 meters. I'll click on Done. The soil is composed of 7 layers, and the thickness of each layer is 1 meter. In order to create the layers of soil, I'll select Partition, then Face and Sketch. I'll click on Offset Curves, select this line, and Done. I'll enter offset distance as 1 meter, click on Flip and OK. I will select this line again, Done, enter offset distance as 1 meter, and OK. I will select this line again, Done, enter offset distance as 1 meter, and OK. In this manner, the thickness of each layer would be equal to 1 meter. I'll click on Done. The soil is composed of 7 layers. The layer 1 is sand and the other 6 layers are clay, which can be observed in this picture. In the next step, I'll enter Property module, click on Create Material. Here I intend to define the properties of sand. I'll select density from the general menu, enter the density of sand equal to 1,900 kilogram per cubic meters, then select elasticity and elastic from the mechanical menu. As described in the book, the Young modulus of sand is equal to 13,780 kilopascal, and Poisson ratio is equal to 0.3. In the next step, I'll select pore fluid and permeability from the other menu. Here I'll enter the specific weight of water equal to 9,810 Newton per cubic meter. The permeability of sand has not been mentioned in Sam Helbani book, so I will enter an assumed number for the sand permeability. I will enter permeability of sand as 6 meters per second and void ratio equal to 0.8 and OK. I'll click on Create Material here. I intend to define the clay layer 1. I'll select Density from the General menu, enter Density of clay as 1900 kg per cubic meter, then select Elasticity and Porous Elastic. In this table you can observe the properties of clay layers. Log bulk modulus, that is displayed by kappa, is equal to 0.01 and enter Poisson ratio equal to 0.28. In the next step, I'll select plasticity and clay plasticity from mechanical menu. Lambda is equal to 0.1174. Stress ratio is equal to 1.5. You can observe the pre-consolidation pressure in this column and the situ vertical effective stress in the center of each layer in this one. Here, since the quantities of the pre-consolidation pressure are more than the situ vertical effective stress in the center of each layer, so the soil is over-consolidated. So that we can use these quantities for calculating the initial yield surface size quantities. Here the pre-consolidated pressure quantities have been divided by 2, and here the initial yield surface size quantities have been brought for the layers of clay. The initial yield surface size quantity for the layer 1 are equal to 18.38 multiplied by 10 to the power of 3 Pascal. Enter wet yield surface size equal to 1, flow ratio surface as 1, 2. In the next step, I'll select pore fluid and permeability from the other menu. I'll enter the specific weight of water equal to 9,810 Newton per cubic meters and the permeability coefficient of clay equal to 6 multiplied by 10 to the power of negative 12 meters per second and enter void ratio equal to 1.5 and OK. In the next step, I will make a copy of this material and name that clay layer 2 and OK. Then I will click on Edit and enter initial yield surface size equal to 27.57 multiplied by 10 to the power of 3 Pascal and OK. Again, I'll make a copy of this material and name that clay layer 3 and OK. I'll click on Edit and enter initial yield surface size as 36.76 multiplied by 10 to the power of 3 Pascal and OK. I will make a copy of this material again Name that clay layer 4, then click on edit and enter the initial yield surface size for the fourth layer equal to 45.95 kilopascal and OK. We will do in such a manner for the fifth and sixth layers. So in this way the properties of all layers was defined. We have 7 layers, so we have defined 7 materials. I'll click on Create Section, select Solid Homogeneous, Continue. Here I'll select the sand material and OK. I'll click on Create, Solid Homogeneous, Continue. Here select Clay Layer 1 and OK. Here I'll select Clay Layer 2 and OK. Here I will select Clay Layer 3 and OK. I should create the other sections in such a manner as well. In the next step, I'll click on Assign section, select the first layer, done. Select the sand section and OK. I will select the second layer, done. Here second, select clay layer 1 and OK. I will select the third layer, done. Select clay layer 2 and OK. I will select the fourth layer, select the clay layer 3 and OK. I'll do the same for the other layers in this manner. So the properties of all layers was defined in this manner, and if I select materials from here, layers will be displayed in different colors, indicating that the properties of each layer are quite different with another layer. I'll enter Assembly Module, click on Create Instance and OK. I'll click on Translate Instance, select the soil. First select this point and then this one and OK. In this manner, the coordinate system will be placed over the surface of the soil. I will enter Step Module. Here I will save the model. And OK. I'll click on Create Step. As described in Sam Helwani book, this question will be done in 3 steps. In the step 1, the effective weight of soil will be applied. Here I'll select geostatic and continue. The step 1 is a geostatic step. The analysis will be done in non-linear form. Here I'll select unsymmetric and OK. I'll click on Create. In the step 2, one strip loading of 100 kilopascal will be applied to the soil. Here I'll select the soils and continue. Time period is equal to 1 multiplied by 10 to the power of negative 5 seconds. Select fixed and enter maximum number of increment equal to 1. Here select unsymmetric and OK. I'll click on Create. The step 3 is a consolidation step. Here I'll select the soils, continue. As explained in the book, time period is equal to 1 multiplied by 10 to the power of 9 seconds. But in the diagram has been drawn here, time period is equal to 1 multiplied by 10 to the power of 7 days. So we should consider time period more than 1 multiplied by 10 to the power of 9 seconds. I'll enter time period equal to 1 multiplied by 10 to the power of 12 seconds. Here I'll enter maximum number of increment equal to 100,000. Initial increment size equal to 0.005 seconds. Minimum equal to 1 multiplied by 10 to the power of negative 8 and maximum equal to 1 multiplied by 10 to the power of 11. Maximum pore pressure change per increment equal to 100,000 Pascal. Select unsymmetric from here and OK. In the next step, I'll enter load module. Click on Create Load. Select step 1 from here, then body force and continue. Here I'll select the whole of the soil. Done. Here we should enter the effective specific weight of soil. You can calculate the effective specific weight of soil according to this relation, in which the effective specific weight of soil is equal to specific weight of saturated soil minus specific weight of water, the quantities of which is equal to 9,190 Newton per cubic meters and OK. Here we intend to apply the strip loading to the soil. Before doing so, we should create partition on the model. To do so, I'll select partition from the tools menu, then face and sketch, select the whole of soil. Done. Here I'll draw 2 vertical lines in this manner. The distance between these 2 points is equal to 13.5 meters, and the distance between these 2 points is equal to 13.5 meters. I'll click on Done, then enter Load Module, click on Create Load. Here I'll select Step 2, then Pressure, and Continue. I will select this surface, Done. As described in the book, one strip loading of 100 kilopascal will be applied to the surface of the soil. Here I will enter the quantity of 100,000 pascal and OK. In the next step, I will click on Create Boundary Condition, select Initial Step, then Displacement Rotation, and Continue. I will select the bottom of the soil, Done, and close the boundary condition of U1 and U2 for it, and OK. In the next step, I'll click on Create Boundary Condition again, select Displacement Rotation, and Continue. I'll select these edges, Done. Close the boundary condition of U1 for it, and OK. In this manner. Here I'll save the model, click on Create Boundary Condition, select the consolidation step, then select Pour Water Pressure and Continue. I will select the top and below surfaces of the soil, and Done. As explained in the book, in the step 3, the pore water pressure of the top and below surfaces of the soil is 0, and the drainage from these two surfaces will become possible. Here I will enter the pore water pressure equal to 0, click on Create Amplitude, select the tabula, Continue. Here select total time and enter the quantities here. And OK, and here I'll select amplitude 1 and OK. In the next step, I'll click on Create Predefined Field. Here, select Initial Step, then Void Ratio and Continue. I'll select the layer 1, Done. Enter Initial Void Ratio equal to 1.5 and OK. I will select the Void Ratio, Continue. Select the layer 2, Done. Enter Initial Void Ratio equal to 1.42 and OK. select the layer 3, done, and enter initial void ratio equal to 1.37 and OK. I will select the layer 4, done, enter initial void ratio equal to 1.34 and OK. I will click on Create, select void ratio, continue, select the layer 5, done, and enter void ratio equal to 1.31 and OK. I'll select the layer 6, done, and enter initial void ratio equal to 1.29 and OK. I'll select the layer 7, done, and enter initial void ratio as 1.27 and OK. In this manner, the void ratio for all layers was defined. Here, I'll save the model, click on Create Predefined Field. Here, select Geostatic Stress and continue. I will select the layer 1 and done. Here, we should enter the initial effective stresses. You can use this formula in order to calculate the initial effective stresses. That's the specific weight of saturated soil minus specific weight of water multiplied by height. The effective stress on the surface of soil is 0 at the depth of negative 1 meter. The stress is equal to negative 9,190 Pascal, and the lateral coefficient will be entered 1 and OK. I'll click on Create Predefined Field, select Geostatic Stress and continue. I will select Layer 2 and done. At the depth of negative 1 meter, the stress is equal to negative 9,190 Pascal, and at the depth of 2 meters, the stress is equal to 2 multiplied by 9,190 Pascal. And I'll enter the lateral coefficient equal to 1 and OK. I will click on Create Predefined Field, select Geostatic Stress and continue. I will select Layer 3. At the depth of 2 meters, the effective stress is equal to 2 multiplied by 9,190 Pascal, and at the depth of negative 3 meter. The effective stress is equal to 3 multiplied by 9,190 Pascal. I'll enter the lateral coefficient equal to 1 and OK. I will select the layer 4, done. At the depth of negative 3 meter, the effective stress is equal to 3 multiplied by 9,190, and at the depth of 0.4 meters, the stress is equal to 4 multiplied by 9,190 Pascal. I will enter the lateral coefficient as 1. OK. I will select the layer 5, done. At the depth of 4 meters, the stress is equal to 4 multiplied by 9,190, and at a depth of 0.5 meters, the stress is equal to 5 multiplied by 9,190, Here I will select the last layer, in the next step I'll enter Mesh Module, click on Seed Edge, select these lines, done, consider 10 elements for them, and OK. Then I will select these lines, done. From here select single, I'll click on select these lines again, and done. I will enter number of elements as 15 and base ratio as 10 and OK. Then I'll select these lines, Done. Consider 3 elements for them, and OK. I'll click on Assign Mesh Control, select the whole of the soil, done. Here I'll select Structured and Quad and OK. I will click on Assign Element Type, select the whole of the soil, done. Put the element family on Pore Fluid Stress. Here select Quadratic and OK. Finally I will click on Mesh Part and yes, in this manner. As you observe, fine mesh has been used in the area where the strip loading is applied to the soil. Here I will save the model, enter Job Module, click on Create Job, Continue, OK, and click on Submit. The analysis was done successfully, so I'll click on Result. Here I'll select U and U2. Here you can observe the vertical displacement. As you see, the final settlement is equal to 7.9 multiplied by 10 to the power of negative 2 meters. That is equal to 79 millimeters. In the step 1, the weight of soil has been applied. In the step 2, one strip loading has been applied to the soil. And here you can observe the settlement caused as a result of strip loading. The settlement is equal to 27 millimeters. In the step 3, that is a consolidated step, the final settlement is equal to 79 millimeters. Here you can observe the pore water pressure. The purpose of this analysis is drawing the consolidation settlement of soil, and actually we intend to draw the related diagram in the Abaqus software. To do so, I will click on Create XY Data, select ODB Field Output and continue. From here select Unique Nodal, then U2. Finally, I'll select this node and click on Plot. Here, I will select these 2 columns, copy, and paste them in the Excel software. The first column is time period, the unit of which is second. and the second column is settlement, the unit of which is meter. As you observe in this diagram, the unit of time period is day, and that of settlement is millimeter. Here I will convert the time period from second to day. So I will divide the quantities of this column by 86,400 seconds. And I will multiply the quantities of this column by 1000 millimeters. In this manner, the first column is time period, the unit of which is day. The second column is settlement, the unit of which is millimeter. As previously mentioned, at the end of the second step, the maximum of settlement is equal to 27 millimeters, and this settlement is caused as a result of strip loading of 100 kilopascal. Therefore, as you observe, the quantity of 27 millimeters here will be added to these quantities, In the next step, I intend to refer to one mistake that exists in the book. As explained by the book, the consolidation settlement has been calculated as 91 millimeters, utilizing the analytical solution. In the table, you can also observe the ultimate consolidation settlement that is equal to 91 millimeters. But according to the diagram having been drawn in the book, the consolidation settlement having been calculated by analytical solution is about 85 millimeters, which has been calculated by mistake and is wrong. In fact, there is a difference of 6 millimeters in the calculation. I will select this column, then this one, and then select this diagram from the Insert menu. Here I will tick on logarithmic scale option in this manner. Here you can observe the diagram of the consolidation settlement having been drawn using the Abaqus software. As you observe, there is a slight difference between the results gained from the Abaqus software with that in Sam Helwani book. The reason is that there is a mistake in the book. That mistake is that in the Sam Helwani book. The final consolidation settlement is equal to 91 millimeters, and in this table the final consolidation settlement has been calculated equal to 91 millimeters, but in the diagram inside the book the consolidation settlement is about 85 millimeters, and that's the same mistake mentioned. Actually, the diagram which has been drawn in the book should be shifted about 6 millimeters downward so that the consolidation settlement will be transferred from 85 to about 91 millimeters, and if this should happen, the result gained in the Abaqus software will be quite identical to those having been obtained from Sam Helwani book.